And we are back, and today we're going to look at RLC circuits, the Schrodinger's equation, and maybe some mechanics problems. So basically, when you're looking at ODEs and PDEs, they're pretty ubiquitous throughout engineering. So if you're looking at circuits and you're looking at Kirchhoff's law, so meaning we need to make sure that the voltages in any loop basically sum to zero, or the currents are effectively equal. You can actually look at an RLC circuit, so resistor, inductance, voltage here, capacitor. You can look at basically looking at solving essentially an RLC circuit. So you can look at several different examples here, and we can see as we change some of these parameters, resistance, inductance, my capacitance, how my voltage and how my current essentially change throughout here, or your inductance as well. So you can actually see some of these inductance values change, and you can see the voltage as well. So it's a pretty fun, as you change that resistance, you can kind of see the change in the response. If you have low resistance, change that inductance, capacitance. So interesting and fun way to kind of play with, you can practice essentially circuits. Schrodinger's equation is a very, very good one as well. So for example, we can look at and solve essentially the time-dependent electron in 1D box. So as a function of, again, second order in space for one dimension, first order in time, I can set my wave function sum to zero. I can solve this function here. Once I get my D solve, I can set up with my boundary conditions, and I can also specify essentially one of my solutions to get. This is effectively my non-trivial solution. And then I can show that if I integrate, essentially, this is going to be my complex conjugate times essentially my wave function, that you can look at in the Schrodinger's equation that if I multiply my wave function here times this complex conjugate here, this will give me my probability distribution. So if I look at my electron all the way throughout my box, D, I must be able to find that one. So you can do very similar things, different boundary conditions. So you can look at a sum of two stationary states, and you can actually look at essentially what does it look like the density of states in my system. So that electron will essentially have a density of states, and actually you can see here the density of states changes and evolves as a function of time, and you can kind of see that here. So the center of the electron, again, the density of states moves from the side to side. So it's moving back and forth in that box. So a pretty fun, again, physicsy type solution that we don't have, unfortunately, time to get into today. You could also look at solid mechanics problems. So when you're looking at essentially modeling viscoelastic materials, you can look at those with basically Maxwell models, Kelvin models, and you can do stress relaxation experiments where you apply constant strain and you measure stress, or creep, constant stress, and you measure strain, and you could essentially solve for how stress will evolve as a function of time, strain evolves as a function of time. You can see here our fundamental expression for our Maxwell and our Voigt models here, and you can start to solve for these problems. And finally, you can look at beam bending. So beam bending is a fourth order ODE, and you can kind of start to see, and we can actually see free beam, no load, unit load, mid load. You can see this Dirac delta function, essentially where we're placing this load. And we can go ahead and actually load our system. So, and you can see some solutions here. So this is our beam equation, so fourth order ODE, and we can set some boundary conditions. So here, for a clamp, we're going to fix the position, and we're going to fix essentially the slope value. So where do we put the clamp? And we're going to fix the angle. You can do a knob, so that's going to change essentially the basically the position. You're going to apply the knob and then the torque. You have a free beam, so basically where your curvature is going to be basically your second derivative, or your moment must be zero, y3 must be zero. No load, again, unit load, mid load, etc., etc., etc. Box load, so some magnitude to it. Linear load, so lots of different ways. So for example, I can look at my B equation, I can apply no load, a clamp at some distance here, and a knob here. And you can go ahead and evaluate essentially this function. So again, beam equation, clamp, specified here at my y value. So we could go look back at clamp. So you specify here, clamp y there. So we're clamping in the y, and then we're going to look at essentially how does it deflect essentially the x? You can use quite a bit and actually look at this. So you can see here I have beam visualization, distributed load. I can look at basically unit load here, clamping it, and then the free beam effective expression. So you could do multiple knobs, so you can look at the deflections here. You could look at box load, so sitting here with a double clamp. So clamp, again, Y, clamp here on the Y at x equals 0. And then you can see here for, remember, go back to your clamp function, position. So I'm setting my position must be 0, my slope must be 0. So I'm clamping it in the Y, and I'm looking at, and then basically varying that function here. So clamp, clamp, free beam on the other axis here. So here I've got knob, knob, so I'm preventing it here. Here I've got a clamp here, a clamp at 1, and then that unit load. You can see I've got mid load here, clamp, knob. You could do, instead of knob, you could do clamp. You could see that function as well and see how it changes. I could do knob, knob. I can set, again, my slope value to be 1 or 10. Actually, that's not my slope value, that's my curvature value, but if I do clamp, clamp for some reason, I can look at that and see those loads. And you can see here, again, load with balancing knobs. So basically 3-point bending here, effectively. So those are some of the many different examples that you can do, essentially solving some of these beam bending equations. So thank you for your interest in the video. I appreciate it, and then we'll see you all next time. Thanks, and on to lecture 8 with fluxes. Thanks. Bye.